What if an AI agent delivers the exact right answer, but it got there by citing a draft policy, claiming completion without proof, and ignoring a critical update that just went live? By traditional metrics, it succeeded. By institutional standards, it failed completely. This is the central problem with how we evaluate agentic workflows today. We measure whether an agent reaches the correct outcome, but we rarely verify whether the authority behind that decision was valid, whether the completion was independently provable, or how later changes propagated through prior work. Correct execution is not governed execution. In this video, we're breaking down a new architectural approach to fixing this gap. We'll look at how a deterministic causal-state layer, called matrix, externalizes provenance integrity around probabilistic agents, what the actual experimental results show when you separate accuracy from governance, and why a critical transfer failure reveals the exact boundary between mechanism fidelity and semantic validity. Let's start with the core framework. The paper defines governed execution as a conjunction of three distinct provenance properties: decision provenance, execution provenance, and change provenance. Decision provenance requires that every action is backed by the current, effective authority and accepted facts. It's not enough to retrieve relevant documents. The system must distinguish between semantically related records and the ones that are actually authoritative and applicable. If an agent cites a draft, an expired waiver, or an adjacent domain exception, the decision is provenance incorrect, even if the final action matches the expected outcome. Execution provenance solves the self-certification problem. An agent claiming a task is complete is just making an input assertion. Governed execution requires that each obligation is tied to a definition of done, and that completion evidence is independently verified against that contract. Failed attempts are preserved, not overwritten, and closure only happens when a supervisor verdict confirms the evidence satisfies the declared obligations. Change provenance handles the messy reality of evolving policies. When a new authority version or fact set is admitted, the system must identify which prior decisions, tasks, and receipts depended on the superseded version. It then invalidates only those dependent objects, preserves unaffected proof, and issues targeted replacement obligations. This prevents both stale residue and unnecessary full system reruns. These three properties aren't just audit trails. They're operational requirements. The EU AI Act and NIST's AI risk management framework both emphasize traceability and documentation, but neither prescribes how to architect it. Matrix proposes a concrete solution, a deterministic substrate that sits around the probabilistic model. Here's the architecture. The system maintains 6 first-class state sets: versioned authority, accepted facts, admitted decisions, issued tasks, completion receipts, and supervisory verdicts. Type dependency edges record exactly which versions were read or produced by each later object. This state is an institutional claim, not an objective truth oracle. Authority can be incomplete, facts can be wrong, and models can misinterpret evidence. The point is to make those accepted claims explicit, versioned, and revisable. The model continues to do what it does best: interpret documents, judge applicability, propose plans, and perform open-ended work. The matrix substrate owns the deterministic mechanics: stable identity, direct references, transition validity, declared preconditions, receipt matching, dependency traversal, and bounded retry counters. This separation means the framework can enforce state transition rules independently of whether the model wants to self-enforce them. The lifecycle follows a strict ordered sequence. First, applicable authority and case facts are recorded, including explicit unknowns. Second, a model-proposed decision and obligation plan is accepted or rejected. Third, tasks are only issued after declared preconditions are satisfied. Fourth, every execution attempt is preserved, with evidence attached to a receipt. Fifth, each receipt is verified against the task-specific definition of done. Sixth, a supervisor emits a verdict with any residual obligations. Seventh, bounded, targeted rework is requested, or escalation occurs when the retry budget is exhausted. And finally, on authority or fact change, dependent state is invalidated, and only the required portion of the lifecycle is repeated. The event log is append-only. A retry doesn't erase a failed receipt, and a replacement task doesn't erase the authority version under which its predecessor ran. Current materialized state and historical reconstruction are simply separate views over the same operations. Now, let's look at what happens when you actually run this against standard baselines. The experiments were deliberately designed to show cases where business outcomes tie, but provenance integrity diverges. In the decision provenance study, both direct retrieval augmented generation and the governed path selected every expected action across 15 repeated runs. Accuracy tied, but direct retrieval cited non-governing records in 6 of those runs. It promoted drafts and expired waivers as if they were authoritative. The governed path, which added an explicit applicability adjudication step before binding facts, cited 0 unsupported records. The governed path used more inference calls, but it enforced citation soundness. In the execution provenance study, both conditions received the exact same agent plan and one generic self-review pass. The self-review successfully produced complete obligation plans. Yet the direct condition still accepted its own unsupported completion claims and self-closed. Matrix, on the other hand, independently compiled obligations, checked preconditions, validated receipts against obligation-specific definitions of done, and refused closure when evidence was missing. It retained the failed attempt, directed a specific retry, and only closed after receiving a complete, current receipt set. Self-review and completion verification are fundamentally different functions. In the change provenance study, a privacy authority version was superseded, changing only one evidence contract. Both conditions were designed to stay current. The direct control, lacking dependency lineage, conservatively reran all 6 tasks. Matrix traversed the declared read dependencies, marked only the affected task stale, and reissued it. Task re-execution dropped from 18 to 3. The difference wasn't accuracy, it was recovery scope. There's also a structural refusal mechanism. A public completeness contract can declare mechanically required authority classes. If the visible candidate set lacks a required class, the framework blocks a confident ruling and makes escalation effective, even when the model never proposed escalation itself. This proves that metadata decidable invariants can enforce hard refusal boundaries without larger models. But here's where the results get critical. The paper includes a controlling negative result that separates mechanism fidelity from contract validity. A deterministic completeness contract was perfectly implemented on the authored test fixtures. It achieved perfect sensitivity on incomplete packets and 0 false escalations on complete ones. But when that same contract was transferred to independently contextualized synthetic packets, it failed catastrophically. It blocked every reviewer complete packet. Sensitivity stayed at 1, but specificity dropped to 0. This isn't an implementation bug. It's a fundamental architectural boundary. Matrix can faithfully enforce a declared contract, but it cannot manufacture semantic validity. A rule can be perfectly deterministic and still be wrong for new data. The contract's notion of completeness didn't transfer because the authored ladders captured structural patterns, not open-world semantic coverage. This leads to a crucial engineering split. Metadata decidable invariants, like missing authority classes or expired policies, can be hard, model-independent gates. But applicability, semantic completeness, and policy conflict resolution that require open-world interpretation remain soft judgments. They still require models or humans. Governance improves accountability and controlled escalation, but it doesn't replace semantic capability. So what does this mean for production AI? It means we need to stop treating governance as a presentation feature or a post hoc audit log. It needs to be a system requirement. The institutional account of work matters as much as the surface answer. An enterprise reviewer needs to establish what authority produced a decision, whether execution actually satisfied its declared obligations, and how later changes propagated through prior work. Matrix demonstrates that you can compose decision admission, receipt-verified closure, dependency scoped recovery, and structural refusal into one bounded lifecycle. But it also shows that mechanism fidelity doesn't equal contract validity. The next validation milestone isn't another accuracy benchmark. It's an independently authored enterprise task where policy owners, packet authors, and audit reviewers are completely separate from the contract designers. The durable claim here is inspectable state and lifecycle integrity. A deterministic causal state layer can preserve decision, execution, and change provenance around probabilistic agents. It allows us to distinguish outcomes that are merely correct from outcomes that are grounded, verified, current, and replayable. As agentic systems move from prototypes to institutional infrastructure, provenance integrity won't be a luxury. It will be the baseline,